A2 Further Maths, Game Theory and Simplex Tableau. Okay, so before we go to some second year stuff, what I'd like to do is just recap a bit of your first year game theory questions. So just have a think about this question. Does this game between Robin and Carol have a stable solution? So just pause there, see if you remember how to show that. Okay, so what we need to do is we need to find out the worst case scenario for both Robin and Carol. What is the worst thing that can happen to them if they play any of their strategies? So if Robin plays a strategy 1, strategy 2 or strategy 3, what's the worst thing that could happen to him? And if Carol plays her strategy 1, 2 and 3, what's the worst thing that could happen to her if she played those strategies? And we do that by looking at the rows to start with. So we can look at the rows, what's called the row minima. And the reason why it's the row minima is because the smallest number on there, the minimum, is the worst case scenario. So Robin could lose 3, he could win 2, he could win 3. Losing 3 is the worst case scenario. So we could put -3 in there. If he plays strategy 2, the worst thing that can happen to him is he could lose 5. So we put the -5 in. And if he plays his strategy 3, the worst thing that can happen to him there is he could lose 3. So we could put in -3. Okay, so this is the worst case scenario if Robin played any of his strategies. Okay, well, we could do the same for Carol, but just be careful because Carol looks at this matrix the opposite way round. This is Robin's grid. Okay, this is all showing about what Robin could win or lose. Carol has to think opposite because she goes across. So for Carol, if she plays her strategy 1, -3 means Robin loses 3, but it means Carol wins 3. So that's a good number for her. Whereas number 3 means that Robin wins 3, so therefore Carol would lose 3. So the number 3 is a negative, is a bad for Carol. So instead of looking at the row minima, we look at the column maxima. We're looking at the maximum value of here because that's the worst thing that can happen to Carol. So if Carol plays her strategy 1, she could lose 3, she could win 3, she could lose 3, or she could lose 1. So this situation here where she loses 3 is what we put in. We don't write -3 or anything like that. We always stick with the numbers that we see here is always to do with Robin, so we don't get confused. What about this one then? Carol plays strategy 2. She could lose 2, win 5, win 3. Losing 2 is the worst, so that's why we put the number 2 in, because that's the maximum out of those. And in this case, number 3 is the maximum. So we have the worst case scenarios for Carol. She could lose 3, lose 2, or lose 3. Now, to have a stable solution, what we need to do is, first of all, we need to work out the play safe strategy for each of them. So if you were Robin and you were thinking, what I need to do is advise him to play one of these, if he plays strategy 1, he could lose 3. Play strategy 2, he could lose 5. Play strategy 3, he could lose 3. You would probably advise him to play strategies 1 and 3 because they're the best of those worst case scenarios. Losing 3 is better than losing 5. If you're advising Carol, you would tell her to play her strategy 2 because if she plays her strategy 2, the worst thing that happens to her is she loses 2. So that's her play safe strategy for that one. Now, if these two values are the same, that's when you have a stable solution. Now, if we look at this situation, the best situation for Robin is losing 3. The best situation for Carol is losing 2. Those two numbers are not the same. So because they're not the same, it has no stable solution. You are looking for these two values to be a stable solution. So it doesn't mean you can't do anything with it. We then have to look at a mixed strategy. If it's stable, it's a bit of a boring game. It means that both players will just play their play safe strategy and then one person will just end up losing all the time, unless it's a 0, of course. All right, so it's a bit more interesting game. It's not stable because the maximum of the row minima is not equal to the minimum of the column maxima. So before we look at the mixed strategies, let's just have a go answering this question. So what strategy should Carol never play and why should she never play that strategy? Okay, so just pause there if you remember how to do it and have a go yourself. Okay, so when we're talking about what strategies Carol should never play, we're talking about dominance. When we talk about dominance, it means that you're trying to play a strategy, or you could play a strategy where another strategy will be better than that strategy in every possible way. Okay, so I'll give you an example. If Carol played her strategy 1, on this first one here, we can see that -3 means she wins 3. So that's good. She wins 3. Whereas on strategy 2, if she had played it, she would have lost 2 if Robin had played her strategy 1. So she could win 3 or she could lose 2. if we're comparing strategies 1 and 2. But then when you look at the second, if Robin had played strategy 2, Carol would have lost 3 there and won 5 there. So they swap places. Win 3, lose 2, but then lose and win. So because they swap over, strategies 1 and 2 are not dominant over each other. Because depending on what Robin plays, these ones would be better depending on what Robin played. Sometimes it's better to play strategy 1, sometimes it's better to play strategy 2. So let's compare something different then. Let's compare Carol's strategy 2 and 3. Now strategy 2 means that Carol would have lost 2. Or if he played strategy 3, she would have lost 3. So losing 2 was better than losing 3 if Robin had played their strategy 1. What about if Robin played their strategy 2 though? Well, in this one, Carol would have won 5, whereas on this one, she would have only won 3. So winning 5 is better than winning 3. Losing 2 was better than losing 3. And so what about the last one? Well, if Robin decides to play their strategy 3 and Carol played this one, she would win 3, whereas on that one she would win 2. Winning 3 is better than winning 2. It doesn't matter which strategy Robin picked, strategy 2 was always better than strategy 3 for Carol. So this is what we call dominant. Never play strategy 3 because strategy 2 is dominant over it. And you should write down each of the examples. 2 is lower than 3. -5 is lower than -3. And -3 is lower than -2. Now because it's Carol and it's the opposite way around, we're basically saying because all these inequalities are facing in the same direction, there is definitely some dominance going on there. So you can ignore strategy 3 completely. And so for Carol, she should only choose strategies 1 or 2. Okay, so it reduces it down to that sort of game matrix. Okay, so what I'd like to do now is try figuring out what the mixed strategy is. Now we can't do that for Robin because Robin's got 3 options. So you can't choose P and 1 minus P. So what we need to do first of all is write the plain math matrix for Carol from her point of view and then find the mixed strategy for Robin. Okay, so I'd like you to have a go at that. So see how far you get, so pause there, see how far you get using the graphical method to find the mixed strategy for Robin. So remember we are looking at Robin in the end. Okay, so we know we can't do Robin straight away, we have to find Carol's first. So we can rewrite the matrix for Carol. Now we can do that by transposing it, so it looks like this, but then don't forget now that Carol's on this side, it should all be about Carol. So before, Carol's -3 was Carol winning 3. So this time, that should be +3. This -3 here is Carol losing 3. So when you write the grid the other way round, this is -3 and so on. -1, 2, -2, +5, +3. So there's the matrix or the game, zero-sum game from Carol's point of view. We need to remember that when it comes to the value of the game. So we've got Robin and Carol set up like that. Now what we can do now, and the reason why we had to set it like that, is we can look at the mixed strategy for Carol, not for Robin just yet. So for Carol, she can play 2 options, either 1 or option 2. Now what we can do is we can look at the probability of playing option 1 as a P, and that means that the probability of playing option strategy 2 would be 1 minus P, because then therefore they add together to make 1. She definitely has to play one of those 2 strategies. Now once we've got that set up, what we can then do is work out all the different inequalities. So we could do that. If we look at Robin, she could win 3 every time she plays P, or if Robin plays a strategy 1, she would win -2 every time Carol plays 1 minus P, and that is the value of the game. So therefore simplify it, 5p minus 2. You might want to pause there and have a go at the other 2 if you haven't done it already. Okay, so you should just work through. So what about if Robin plays their strategy 2? Well, if Robin plays their strategy 2, you would lose 3 every time you play P, but you would win 5 every time you played the strategy 1 minus P. And again, that would equal the value of the game. So therefore we can rewrite that, 5 minus 8p equals 3. And then you could finally do it for strategy 3. What happens if Robin plays their strategy 3? Well, you would lose 1 every time you play P, and you would win 3 every time you play strategy 1 minus P, strategy 2. And so therefore 3 simplifies to 3 minus 4P equals V. Now once you've got those set up, what you could definitely do now is plot those graphically. And this is very similar to the graphical technique for linear programming. So we can just rewrite them in. We're going to have a look at 2 points to help us plot it, but also look at 2 points to help us plot the graph as well. So if I look at when P equals 0, I know V equals minus 2, and when P equals 1, then V equals 3. Of course, looking at the 2 extremes of the probabilities. I'll do the same for this one. So P 5 minus 8P equals V. When P equals 0, I get V equals 5. When P equals 1, I get V equals minus 3. Okay, so it's going to give me 2 points to plot in a minute. And the same for this one. When P equals 0, I get 3. And when P equals 1, I get minus 1. So I could draw my number line going across, and I could draw my value of the game going upwards. I can see that I don't need to go any lower than minus 3. So I can go to there. And I don't need to go any higher than 5, because 5 is the highest one out of all of them, to there. So now that I've got that, let's just go through and plot each of these lines. So for strategy 1, it would have been this sort of line, just like that. And for strategy 2, all right, making sure that I'm writing down which one's which. For strategy 2, it's going to go something like that, 5 minus 8p. And then finally, for strategy 3, it would look something like this. Okay, so 3 minus 4p equals v. So I've got all my strategies set up. I've graphed them all. And now I want to be still doing a play safe strategy. Right? It's no good at looking at this graph and thinking, well, if I played P equals 0, in other words, played strategy 2 all the time, that'd be great because I could win 5. But you could also only win 3, or you could also lose 2. Now, lose 2 is the most important one because you are still playing safe. So you're looking for the least values all the time. Now, if you changed your mind and played P as maybe 0.2, 1 in 5 games, you could still win this, you could still win this, but most importantly, you could still lose 1 each game. So you're looking for always picking the bottom of them all. When I get to this point just here, there's a swap over. Suddenly this game here is the worst case scenario. So what I should end up with is a pattern that fills in the bottom of the worst case scenario. Now in this case, we can see that this strategy here should never be played. All right, it'd be foolish to play their strategy here from Robin's point of view. So what we'll probably find later on is that this graph that got us this one, which was strategy 3, we'll probably find that Robin should have that as 0. Should never bother playing it. Right, we'll see that coming up later, most likely. Right, for the rest of it though, we can see that the best out of those worst cases is this point just here. Now we can solve that simultaneously. So I can see it's that graph and that graph. You can set them equal to each other. And then once we know what that value is, we can figure it out by using simultaneous equations. P is going to equal 7/13, and the value of the game will be 9/13. So if you're going to put it in simple terms for Carol, you would say to Carol, roughly every 13 games, you should be playing this strategy here, strategy 1, about 7 times, and for the other strategy, you should play that about 6 times. So roughly 50-50, but not quite. Okay, if Carol did that, then on average she would win 9 out of 13 every single game. Actually, it would be in her favour. Okay, now that's all stuff that you knew from last year, nothing different. The problem is we haven't answered the question yet. That's the mixed strategy for Carol. I want the mixed strategy for Robin. So how do I go about doing that then? Well, the one thing we know that is definitely consistent is the value of the game. The value of the game does not change between Carol and Robin. There's no way that Carol, who's going to be winning 9/13, that means that Robin will be losing 9/13. They are linked together. They can't be different. Okay. So now that I know the value of the game, then I need to look at what variables I don't know. Now for Robin, because he's got 3 strategies, he'd be playing P, Q, and then for the third one, 1 minus P minus Q. Right? Because again, they add up to be a value of 1. I could do the same sort of situation using the equations. What am I going to win? Well, if Carol works out on strategy 1, all right, then I'm going to be getting, let's just go through it. If Carol plays on strategy 1, I would win 3 for every P. Or sorry, it would be lose 3 because it's Robin's point of view. He would lose 3 for every P. He would win 3 for every Q. He would lose 1 for every 1 minus P minus Q. Okay, so you're still filling in exactly the same, like that. And we know this is going to equal 9/13. So unlike before, when we didn't have this as a variable, now we know it. So the only 2 things we don't know is P and Q. Carol plays the strategy 2. Yeah, simplifies that. Carol plays the strategy 2. And that's going to go to this. And so therefore, we also know this is going to equal 9/13. You can see it's minus 2 for every P, 5 for every Q, 3 for every 1 minus P minus Q. That simplifies to this. Now, because I've got these 2 simultaneous equations, just here, these 2 equations, I can solve them simultaneously, and I get P equals 8/13, I get Q equals 5/13, and I've noticed that 1 minus P minus Q comes out to be 0. And we saw that on the graph anyway, but now it's been confirmed algebraically. So for every 13 games, they should play strategy 1 8 times, strategy 2 5 times, and never play strategy 3. No point in playing strategy 3. It's not because it's dominant or anything like that. It's that it's always going to be better to play one of these 2 instead of that. Okay. Right, so there's nothing new there. Everything you've just covered should have been at the very top end of what you covered in your further maths in year 1. And what we want to do is look at solving problems when you can't do it graphically. What happens if you had a 3x3 grid and there was no dominance going on? And so therefore you wouldn't be able to solve it because you wouldn't be able to produce very neat 2 equations with just 2 or 3 unknowns. So what we need to do is we need to look at another way of solving more complicated games. Okay, so let's move on to something new then. So I'd like to just grab your notebooks because we are going to cover this a new section of how to solve higher order games instead of having a situation where we just have 2 possible strategies. Therefore, we can use P and 1 minus P. What happens if we have games which have 3 or more strategies? So we're going to look at situations like that. So in this case, if a zero-sum game can be solved using linear programming, so we can use linear programming to solve zero-sum games that have more than 2 strategies. But to do that, we need to convert it, convert the actual game itself so that each of the cells has a positive value. I'll explain the reason why that is the case in a minute. So for example, if we're going to look at this game, now we've already got the answer to it, of course, and we solved it using Carol to get Robin's answers, but we're going to have a look at just doing it straight away from Robin's point of view. Now the problem is, first of all, is we can't use linear programming to solve this matrix because it has some negatives. Now we need to convert this matrix then, this game here, so that every single value is positive, not 0, but positive. So the only way I'm going to do that is by adding a set constant to each of these values. Now you can see that -5 is the worst one. Now to get that as a positive number, the smallest positive number being 1, I can add 6 to it. Now if I add 6 to that cell, I also need to add 6 to all the other cells. It doesn't really matter what you add. Adding 6 is the smallest value. You could have added anything bigger than 6 and it would still work. Okay, 6 is just the easiest one because that makes everything positive then. So if I add 6 to everything, you can see that I've got -3 plus 6 is going to be 3, 2 plus 6 is going to be 8, and so on. 9, 1, 7, and 3 again. Oh look, everything is positive now. So that means that I can start to think about how I can solve this using linear programming. All right, I'll come back to the reason why that's important in a second. Now we know that if we're trying to solve this using linear programming, we're going to call the value of the original game P. All right, we think of P as our profit. That's what we're looking at. The value of our game is going to be P. Now that means that the value of this augmented game, this one that we changed here, will be P plus 6. So the value of our new game is going to be the original game, plus an extra 6. Now that means if I solve the answer to this and I find out what the value of this game is, I could very easily find the value of the original game because I can just take away 6 from it. P is just going to be the value of this game minus 6. And again, I'll talk about why it's important to be positive in a minute. But doing that conversion means it's very easy to figure out what P is at the very end. Okay, so make sure you pause if you haven't got that down in your notebook. Right, so we noticed that we changed it because we wanted to make sure that our value of our game is greater than 0. So the value of a game is always going to be greater than 0. And that's going to be important because V is one of the variables. P is our profit function. Okay, that's what we're going to be trying to maximize. We're going to maximize P. But to use linear programming, we must make sure that every single one of our variables is positive. Now in this case, if we hadn't have added 6 to everything, then our V value would not be positive. But now we know it definitely is, because every value in our game is positive. All right, even if Robin plays that one all the time, it's always going to be winning 1. It's always going to be a positive value. There's no way that Robin could lose on this game. Okay, and that's what we wanted to set. So the reason why we make it all positive is because we know now that the value of the game is definitely greater than 0. One of our variables is definitely greater than 0. Now the reason why this is important, so you will remember that if we're solving linear programming problems using the Simplex Tableau, all the variables must be greater than 0 to be able to use the Simplex Tableau. Right, our goal is to maximize the P value, right? Because that's the previous game. We're trying to maximize the value of the game for Robin, right? What's the best Robin can do? And so we can work that out by saying the profit is just going to be V minus 6. Very simple rearrangement of that. We can work out the profit of the original game because we can get the value of this new augmented game and take away 6 from it. Okay, so that's something you have to do every single time. Make everything positive. Think about the constant you've added and then rewrite the profit function by taking away that constant. Okay, again, just pausing if you need more time. All right, so what we've got so far is we've got this situation. All right, we know that Robin can play strategies 1, 2, and 3. We also know the value of the game is P equals V minus 6. We talked about that a minute ago. All right, the value of the game is P plus 6. So how can we work it out? Well, normally we'd be doing P 1 minus P or P Q 1 minus P minus Q. Now we're not going to do that because we've got more than 2 strategies, 1, 2, 3. All right, or it could be 4, it could be 5, it could be any amount. What we're going to do is just going to attach P1, P2, P3, and so on to each of Robin's choices. All right, so we know, or we can add probabilities P1, P2, and P3. Now we know that P1, P2, and P3 must add together to equal 1. All right, Robin must play one of those strategies. Okay, so we know that is definitely true. All right, and if you'd had more strategies, you'd have P4, P5, and so on. It'd add together to always equal 1. Now, because we're setting up a linear problem, this needs to be one of our constraints. Now, to be a constraint, as you remember from our linear programming problems, this must be an inequality, all right, as opposed to an equation. All right, our constraints are always inequalities. Now, although it doesn't seem to make much sense, what we can do is we can say that P1, P2 plus P3 is always less than or equal to 1. All right, you might have a situation you could argue that it chooses not to play that round, and therefore P1, P2 plus P3 doesn't equal 1. All right, now our goal, of course, will be to get this as close to 1 as possible, and it will always be the case that P1 plus P2 plus P3 equals 1 in the end. All right, but just because we need to set it up as a linear programming problem, the first thing we're going to do is just rewrite it as a constraint. So that's the first constraint we got, that P1 plus P2 plus P3 is definitely less than or equal to 1. Also, we know that P1 plus P2 plus P3, or sorry, P1, P2 and P3 are all positive numbers. They're all greater than or equal to 0. So that's a good thing because the Simplex Tableau has to have positive values. That's why you don't need to worry about setting them greater than or equal to 0. Right, so the other constraints we got can be found using the same technique that we found before. We think about what Carol can do. Now, if we think Carol plays her strategy 1, what would we win? So if Carol plays our strategy 1, yes, we could just say the value of the constant there is always going to be greater, never lower than the value of the game. All right, so you wouldn't want it to be value. So we notice that P1 plus P2 plus P3 is always going to be greater than or equal to the value of the game. You can never get less than the value of the game because we're trying to maximize it. But it could be greater if Carol does something different, if Carol does something wrong. All right, if you're playing against someone that doesn't really understand games, then what you might end up with is a situation where Carol makes mistakes, in which case you get better than your V. Now you're playing from the point of view that you're advising Robin, and Robin knows what he's doing, so therefore he would never get less than V. All right, so the constraint is always greater than or equal to the value of the game. If Carol plays her strategy 2, you'd get 8P1 plus P2 plus P3 is always greater than or equal to V. So a little bit different, a little bit more unusual, but you've almost got to learn this as an algorithm. You've got to make sure you can set up your profit function. You can make sure you set up your constraints. All right, always less than or equal to 1, always greater than or equal to the value of the game. So just remember those key facts. Okay, again, what's in your notebook, just pause there. And as I said earlier on, you don't need that in your notebooks, but as you're maximizing your V, this means your P1, P2 is always equal to 1. All right, because if you reduced P1, P2, P3, it would lead to a reduction of V. Imagine if you chose not to play around, then you would definitely lose money doing that. All right, so you definitely wouldn't have those being less than or equal to 1 if you're maximizing your V. Okay, so now we've got our linear programmer set up from our grid. You can see now it looks very similar to the sort of question you might have back in the Simplex Tableau or graph theory. All right, now if you're going to try doing it as a graphical method, you can see the problem straight away. You've got 3 variables. All right, so you've got X, Y, and Z, so to speak. Now, because you've got X, Y, and Z, then you can't plot it graphically. So we are going to have to look at doing it using the Simplex Tableau. So the first thing we need to do for our Simplex Tableau, we make everything equal to a value, equal to a number, and also consider getting rid of these inequalities by using slack variables. Noticing that P1, P2, P3 and V are all greater than 0, so it means I can definitely use the Simplex Tableau technique. So how do we change it to a Simplex algorithm? So change the objective functions constraints to be into equations using slack variables if appropriate, and remember that they're all equal to a value. So this one can be rearranged by taking the V over the other side and getting that. So P minus V equals minus 6. Remember, it's a P that you always keep as the positive value. All right, so although for neatness you might think, oh, I'm going to take the P over this side and make 6 on this side. No, because it's the P value that you always want as a positive. All right, so the P value is positive, so therefore that's what it looks like. Second one, how do we get rid of this inequality? We can add an extra slack variable. All right, so plus S is equal to 1. Now, ideally, that S value will be 0, and it will be 0 at the end. Okay, don't add it in just yet. This one is greater than V, so in other words, these are going to be bigger than V, so therefore I'd have to take away a slack variable in that case. All right, or the other option is to take everything to the other side and add the slack variable. It doesn't matter which one you pick. All right, so just be aware, especially if the examiner set the question up, all right, and written it like this, you're not looking at it thinking, oh, that's not the way I got taught. It doesn't matter which way round from the inequality you do it. Now, because I've decided to keep the V as a positive and bring everything to this side, all right, that means that it's got 0 on this side. This is less than 0, so therefore you add the slack variable. There's nothing wrong with you keeping it the same way. You would have had minus V minus T. It would have worked out the same. Okay, same one with this. Gets this. Now this is just because this is standard to write it this way around, but if you do it the other way around in your exam, you would not lose any marks. It's still correct. Okay, so again, pause in there. Maybe if you fancy it, you could have a go at the Simplex Tableau yourself now. All right, you don't need to wait for me to go through it and see how you get on. Of course, you already know the answer because we looked at it graphically earlier on. Okay, so pause there if you need more time. Okay, so now I've got these set up, let's put these into our table. So into our table, we can put on our top line the profit function. That always goes in the top line. So looking at this, I can see that I've got 1p, I've got minus 1 for v, and I've got minus 6 my value, and I'll call that equation 1. This one, I've got 0, 0, 1, 1, 1, 1s equals 1. That's my equation 2. Okay, as long as you've got your profit line on the top, it doesn't really matter which order you put these three. This one's got 1v, it's got minus 3p, minus 2, 9p squared, p2, and so on, all the way across, equals 0. And then the bottom one, 1 for that, minus 8. If you'd done the other way around, all that would have been different is that would have been minus, plus, 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 minus. It would have got the same answer. Okay? Right, so now I've set my Simplex Tableau up, I can now start looking and thinking, do I need to do another iteration? Now we can see it's not optimal yet. It's not optimal because there is a negative in that top line. There's only one negative value, so that makes it very easy to know which column to pick as your pivot column, and then you need to find the ratio test to find the other, find out which is our pivot row. So let's start with this. This is our pivot column because it has a negative in the top line. I've got two choices, these two. I ignore zeros or negatives, so I don't need to worry about the 0. All right, but I do have these two number ones. Now notice the problem. If I had kept these two as negative a minute ago, I would have minus 1, minus 1, minus 1, and I wouldn't be able to find a pivot. So it's absolutely vital that I set it up like this. So earlier on, I said it doesn't really matter, right? And I stand by that. It is the same. What you'll notice is as soon as you put it in the table and you realise here, oh my word, I can't do it. What you can do is you could just go through and change it to positive, negative, 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 positive. You could literally just go through and change it at this stage. Same with this one. All right. So if you forgot earlier or didn't realise it's so important earlier, it's obvious now when you tried to do your ratio test. Okay. But you could also argue it doesn't really matter. You can see why, because they're both zeros. Both zeros, so you've got 0 divided by 1 is 0, 0 divided by 1 is 0. If they were minus 1s, they would still both be zeros. But the rule is, with Simplex Tableau, you ignore zeros and negatives when it comes to your ratio tests. Okay, so what do I get then? Well, I get these two zeros. It means it doesn't really matter which one you pick, right? You can pick either of them to be your pivot row. For argument's sake, I'll pick the top one. Okay, so I've picked this. What do we need to do though? That needs to be number 1, which already is. The rest of them have to go down to 0. So in other words, this is already sorted. It's already got the number 1 there. Okay, this has already got 0. So this column, sorry, this row will be the same as well. So equation number 2 and equation number 3 will not change. Equation number 4 though, that's got to go to a 0 and that's got to go to a 0. Okay, right, so let's perform the iteration, go through it and make sure you're happy. So let's look at that top line then. So the top line, this has to become 0. So the way I can do that is say that equation number 5, I think, first of all, I'll just put my pivot row in. That's going to be the same. Okay, so we always use our pivot row first. So we can say, right, what can I do with equation number 5? Well, that's going to equal equation number 1 plus 1 lot of the pivot row. So it's just going to be that column, sorry, that row, plus that row. 1 plus 0, 1, minus 1 plus 1, 0, 0 plus minus 3, and so on all the way across. A lot more negative than the top line now. Equation number 6 is the same, so I can ignore that. It's just going to be equal number 2 because it's already got a 0 there. Perfect. And for equation number 8, that's going to be the same as equation number 4 minus 1 lot of the pivot row. All right, so we've got that column, that row just there, added, taken away, sorry, from that row just there. So what do we end up with? Minus 8 minus minus 3, so it's minus 5. Minus 1 minus minus 9 is 8, and so on, all the way across. Right, so there we go. I've done one iteration. Is it optimal yet? No, because you've got negatives in the top row. So therefore, we need to do another iteration. Now, this stage, it might be worth just pausing and you having to go an iteration yourself to practice your Simplex Tableau. All right, and you can check with my answer. If you're not feeling comfortable, you might want to see me do another iteration first. Okay, so this is our stage we're at the moment. That's our equations 5, 6, and 7, and 8. And we're going to look at doing another iteration. So we've got another 4 lines, and we take our top line, and we think to ourselves, we've got 3 choices here that's stopping it being optimal. The -3, the -9, and -7. The value of the game does not matter. That doesn't come into it. It's just the variables. Now the -9 is the biggest negative. So that's the one I'm going to use to cancel out the others. That's going to be my pivot column. All right. There's no rule to which one you have to use, but generally speaking, go for the biggest negative. When I look down the list to do the ratio test, I notice there's 2 choices. The -9 I ignore. I could have number 1, which is 1 divided by 1, or I could have number 8, which is 0 divided by 8. So I look at my ratio test, I write it down just to the side. 1 divided by 1 is 1, 0 divided by 8 is 0. 0 is the smaller out of the 2 numbers. So my ratio test is telling me that this is going to be my pivot row. That's my pivot. That's the one I need to get down to 1. So a little bit more interesting now. We get some fractions coming into it. How can I get 8 down to 1? I divide it by 8. So equation number 12 is an eighth of equation number 8. Okay, so equation number 8 divided by 8. So I can go through, make it nice and easy for myself, keep it in fractions, use your calculators. You can see that I've just gone through and divided everything by 8. And now what I need to do is go back to each of the other columns and make use of this pivot row to cancel them down to 0, 0, 0. So how can I do that? Well, the top line, I need to add 9 lots of the pivot row. So equation number 9 is going to be equation number 5 plus 9 lots of that pivot row. All right, to cancel that -9 out. So if I do that, I get 1 plus 9 lots of 0, 0 plus 9 lots of 0, -3 plus 9 lots of -5. Okay, still see I've got actually 3 negatives on that top line again. Right, that's cancelled out. -7 plus 9 lots of 12, not quite enough. Still got what, 2.5. 0. Now this is messed up then because this has got a negative in the top line, and then this one has got to 9/8. -6 plus 9 lots of 0, -6. Okay. Well, what row 10? Well, row 10 is going to be the same as row 6. It's an equivalent position, but it needs to go to 0, so I need to take away 1 lot of the pivot row. So it's this column, take away this one. So 1 minus -5/8 is going to be 13/8, or 1 5/8. 1 take away 1 is 0. Good, that's what you wanted. 1 take away a half is a half. 1 take away 0 is 1. 0 minus -1/8 is +1/8. 0 minus an eighth is -1/8, and 1 take away 0 is back still 1. Okay, so there we go. I've got that column row drawn out. This one's similar to the top line in that I've got 9. So how to get rid of 9? Add 9 lots of the pivot row. So go through. All right, trust you to be able to just do it on your calculator. You should have got some results similar to that. And as you can see, it's not optimal still. All right. Now, if you're in the exam situation, it's highly unlikely the examiner will expect you to do this many iterations. It's more likely that they would get to a situation where they expect you to do 1 iteration and then give you the final solution later on. All right. And if you had it on a computer, you could just get it to run a computer program. But for practicing, it is good for you to practice your iterations anyway. So if you haven't done one yourself yet, pause here, have a go at doing the next iteration yourself. Okay, and I'm going to run through the answer with you now. Okay, so it's still not optimal because we've still got 3 negatives on the top line. So what we're going to do is we're going to have another go. We're going to just rewrite that one out. So there we go. I'm going to be going for the -69/8 because that's the biggest one. Okay, if you'd gone to the other 2, you could have still got it to work. Once I've got that, this time my ratio test you can see is 1 divided by 13/8 is the only choice because these 2 are negative. We ignore negatives. So just be very wary. You can ignore the zeros. All right. If you chose one of those 2, you would have got it wrong. We're choosing this one because it's the only option there is, because it's the only positive value. Right. So I've got 13/8. Now, because I've got 13/8, I need to change that to 1. How can I do that? So 13, 14, 15, 16. I can multiply by 8 over 13, okay, or divide by 13 over 8. Either way round. Right, so if I do that, go through, divide everything by 13 over 8, get those set of answers just there. Same idea as before, very messy though. Use that column to cancel out the others. So how can I get rid of minus 69 over 8? Well, I'd need to add 69 over 8 lots of that one to it. So row 13 is the same as row 9 plus 69 over 8 lots of the pivot row. All right, looking for that pattern. You can see the same pattern comes out. These numbers here are just going to be these numbers just here. Right, so get your calculator. Don't try to do it in your head. Just go through 1 plus 69 over 8 lots of that, 0 plus 69 lots of 8 is 0, that plus 69 lots of 8 of 1, so this is really straightforward, 1, 0, 0. This isn't going to change either, it's going to be 0, but this one will. So minus 5 over 2 plus 69 over 8 lots of 4/13. So loads of fractions going on, so make sure you do it correctly, and you would have got the 2 1/3. 2/13, sorry. Blah, 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 getting all the rest of those fractions sorted. Use your calculator, try not to make any mistakes. Right, once you've got that one done, same with this one. How do you get that minus 69 over 8? You add 69 over 8, lots of the pivot row. That's why it's always the same pattern, because that's number 1. So you can go through, take this row just here, which is equal to 11, add 13 lots, add 69 over 8 lots of this row to it, and you should have got those sets of numbers just there. Okay. Finally, this one here has to go down to 0 as well. How do I get minus 5/8 down to 0? Well, I'd add 5/8 lots of 1 to it. So I can see I've got row 12 plus 5/8 lots of our pivot row. So plus 5/8 lots of that. And as I go through, lo and behold, I get these sets of answers. Now what's quite nice is even though there was 3 negative values on the top line just there, I have now got an optimal solution. So I can see this top line is all positive. Forget the value, all the variables are now positive, so I've finished. So I've got an optimal solution. So very well done if you managed to plug your way through all that, because the top line is all non-negative. Right, so what does that mean though? Well, once you've got the top line as non-negative, we can now solve it. Just pause there if you need more time to write anything down. So just put that last iteration back on. So this is our this is our final solution. So how do we read this then? Well, now we can convert it back to two equations. So that top line, we can see we would write it as P plus 2/13 of P3 plus 69 over 13S plus 7 over 13T plus 6 over 13U equals minus 9 over 13. All right, so I can write that down as an equation. Now what that means is that if I want to maximize my profit, the P3, the S, the T and the U must be equal to 0. Because if I've written it correctly, minus 9 over 13 is the best solution, but I'll be taking away some of these bits. Now you don't want to take anything away from it. It's already bad enough being minus 9 over 13. So don't take anything away. How do you do that? Well, you set all of these variables equal to 0. And hopefully by now you've practiced Simplex Tableau enough to realise anything left positive on this final iteration has to mean that these variables are set to 0. Okay, so what does that leave us with? Well, the P will equal minus 9 over 13. Now, because these are all 0, I can pretty much ignore those bits just there. Really, I'm just concentrating on what's not been done yet. P1 is going to be equal to one lot of P1 is equal to 8 over 13. The value of the game is equal to 69 over 13. Not that that really matters, right? Because that's the value of the augmented one. But notice, interestingly, if you take away 6 from this, you get that. P2 is equal to 5 over 13. So I've got these two probabilities. Now we know they're correct because we've seen them in the previous graphical method. But that graphical method wouldn't have worked if we had a 3 by 3 grid. This one would have done. Okay. all the other variables are equal to 0, all right, except the v value, because that is linked to the p value by adding 6 to it. Okay, right, very well done. That's not easy going for that simplex tableau from game theory, and if they are mean to you and link it in the exam, they will give you some help in hand with some of the iterations. Right, be a good idea for you to have a go at practicing. So you've got your textbooks, so it'd be worth just practicing some of the exercises on page 6.4.